Here is another 2 meter FM transceiver. Can't remember where I got this one. It's been probably a couple years for the whopping sum of $5. Hamfest special, of course. Guaranteed not to work. Although sometimes you can get surprised here. Sometimes just cleaning up the switches, contacts, and general inspection, you can find a few minor things and they work. Although generally they need work. That's when they make it to the $5 bin. But anyway, this one is fairly old. But what I like about it is it's not crystal controlled. It has a crude early phase lock loop in it, synthesizer, and this will transmit between the whole 2 meter band, 144 to 148. It has a power output of either 1 or 25 watts. You can operate split. It has a switch that says repeater, and by pushing this switch you can transmit into a repeater. It will transmit plus or minus 600 kilohertz, which you can select here, minus or plus. It doesn't come standard with a PL tone board in it, unfortunately, but that could be easily rectified with an outboard tone encoder. I did find a manual for the Midland 13510 without the A. So hopefully they're similar here. This is a manual. Here's a spec sheet here if you want to look at it. I thought this was interesting. Deviation adjustable between 3 to 16 kilohertz. Boy, that'd kind of irritate your neighboring channels. 16 kilohertz, but uses a regular dynamic 600 ohm mic. There's a mic connector on the back here. But something I found interesting, according to the manual, there's an accessory jack on the back here. According to the manual here, that accessory jack has these connections. In pin 5 it says tone audio input. Although it says the accessory jack accepts 7-prong plug supplied for tone burst and discriminator meter. Well, it says tone burst, so I don't know if a PL tone, which is going to be a subaudible tone, would be allowed to be inputted through this connector here. I can try it. So if I want to use it on a repeater, I'll either have to add an external tone board internally, or if it works, I'd like to use this jack because then it'll be easy to change the tone. Like I say, I don't know if this works or not. I'm going to hook it up to a supply, current limit supply, and we'll see if we get any life out of this thing. First I'll open it up and do a visual inspection, and we'll see if we find anything that looks either obviously bad or maybe some possible modifications. Sometimes, you know, you find mods in them. But anyway, I'm going to open it up and we'll take a look inside. We'll do that next. Here's a view on the top of the unit here. Of course, the antenna jack in the back, antenna connector comes in. This is called the APC unit. I believe that stands for automatic power control. I'm not sure, but anyway, the signal coming in here is switched between the receiver and the transmitter output, and usually that's done with pin diodes on these units. In the old days they used to use a relay. More modern units will use pin diodes, which automatically switch the RF. Anyway, that's the APC unit where the RF comes in. The one next to it here is the final unit. This has your final amplifier stages with the heat sinks in the back. Here's the RF unit here, So the APC unit here feeds the RF unit through here. Let's see, this stage here would be the driver unit. This is the stage that drives the power amplifier and the output here. Under here is the VCO of the unit. And here I see they've got a bunch of wax poured around here, which can be a problem. Here's the counter unit that drives the display. And that's the top of the unit here. Here's a view of the bottom of the transceiver. Here's the power supply here, where the power comes in through this jack here. It's fed. It's got a regulator, 5-volt regulator for the ICs, and then the 13.8 for the rest of the circuit. This unit here is the AF unit, or the audio frequency unit here. Next to that, over here, is the IF unit, your IF stage. And in front here is your local unit. The local unit here is part of the phase lock loop. And in the olden days, instead of one chip to do all the work, this is done the old-fashioned way with discrete components here. Makes the circuitry a little more complicated. Anyway, that is a physical review of the transceiver here. Next, I'll go over a brief description of the circuitry here before I power it up. So that's coming up next. Stand by. This will be a brief description of the circuitry used in this unit here. This is the RF section here, where the antenna comes in on J101, goes through tuned circuits here in the front. You got L101, L102, then it goes into the first RF amplifier, Q101. Here it's amplified. The output is connected to a 3-section helical resonator here, FT101, which filters the incoming signal. Then it's applied to Q102. This is a dual gate MOSFET mixer, and this mixes the incoming signal coming on the lower gate with the VCO signal that is on the upper gate. And the VCO comes in, and this transformer L104 is tuned to that frequency, applied to the front gate here. And then the output here, this is a mixer. Q102 mixes the incoming and the VCO, and that is tuned by L103, and that's connected to the IF out here that goes on to the IF stage. The signal from the RF deck comes in through this connector, J151, amplified in this first IF amplifier, Q151, and then the output of Q151 is mixed with a local oscillator signal here. This produces your second IF of 455 kilohertz in the mixer Q152. So the output of that is run through this filter here, ceramic filter, and from that point it's run through the IF amplifiers here. These are ICs, IC151 and 152, and this amplifies and limits the signal. The output of the IF amp goes through the discriminator here, where the signal is converted back to an audio signal, and then that's connected through the audio out terminal on J152 here. It says audio out, and then that's run into the audio amplifier. The audio signal is amplified by Q203 and IC202, and then the output here is connected to the speaker. On the left here, input noise is amplified in this chip, IC201, and that drives Q201. And what this does is, when there is no signal, it cuts off the audio coming into the audio amplifier through this transistor here. What happens is the noise level comes in, it's rectified and filtered, and this DC voltage will run this transistor. When this transistor turns on, it basically shunts the audio to ground, which silences the receiver. and that is how the squelch system operates. I'm going to briefly go over the PLL, the phase lock loop that's used in this unit. Now this is an early unit. Before these radios back in the early 70s were made, you had to have 2 crystals for every frequency, basically. Or they had some mixing schemes where it was less. But anyway, you needed a lot of crystals to get a lot of frequency. So once solid state technology was developed to the point where they could build a phase lock loop that you could actually afford, they were done with discrete components. So unlike your modern radios that have the phase lock loops are part of a LSI circuit, everything's generated, you know, within a large scale integrated circuit. All of this was done with discrete transistors and switching diodes and things like that. So anyway, going through this unit here, this is called a local unit. Now this manual I have is for the non A unit. The one I have goes from 143 to 148. This one has, you can see it's, well, if you can read it, it says 144 to 146 and 146 to 148. So anyway, what you're doing here is they're switching in one of 2 crystals here. One is for the lower part of the 2 meter band, and one's for the higher part. So that's done by these switching transistors. They switch in this crystal or this crystal into this oscillator here. Now if you look over here, there's also some other circuitry. What this is for is to offset the frequency by 5 kilohertz, I believe it is. They'll connect a voltage in here, and that will forward bias these switching diodes here that add some capacitance, and that would offset the frequency. Kind of crude, but it worked. Then after that oscillator, it runs through a tripler and then another tripler, and then it's applied over here to a mixer. Q256, this is your PLL mixer here, and that will take that frequency and the frequency of the VCO and mix it together, and the output, it's amplified here, and then the output here is between about 4 and 5 megahertz out on J, if you can read it here. I can't. 2 whatever. Anyway, this is the output here. Now this next section is the counter unit, and this is where some of the magic is done here. That 4 to 5 megahertz signal is input here, amplified by 304, 303, and then it's applied to IC 304. This is just a JK flip-flop, and that divides that frequency in half. That frequency is applied to this integrated circuit over here. I couldn't find any documentation on this one, so if this chip is no longer produced and long obsolete, if this goes bad, you're kind of out of luck. But anyway, this is a programmable divider that's used in your phase lock loop. And you know how they use a reference oscillator. In this case, that's generated over here, a 10.24 megahertz crystal oscillator. And then by dividing that signal, it's processed and divided, that's used to control the VCO. Now this chip here, I did find some information on that one, IC302. Now this chip is a phase and frequency detector. This unit here is the VCO unit, and that output from the counter above is coupled in here. It's amplified by Q351, 352, and 353. And these, as you can see here, this is a low-pass filter, and that's applied to the VCO here. This is the voltage-controlled oscillator. The output of the VCO is coupled down here to Q316, where it's amplified, and then the output here is tuned, and that is the local output here that goes to the local unit up here, the local unit, the VCO input here. It goes into the mixer. At the same time that VCO output is connected to Q355, it's amplified, and then output through this transformer. This provides the oscillator signal for the receive local oscillator and the transmit oscillator on this output here. Back to the AF unit here, there's a number of crystals here that are switched in depending if you want to have a plus or minus 600 offset. These switching transistors switch in different crystals here, and then they're fed to this oscillator here, and then the output of that is sent up to the driver. Now this is the transmit driver stage. That offset oscillator that is from the AF board and the VCO signal from the VCO go through this balance mixer here, this comprised of two dual gate MOSFETs, and they're mixed together. This produces your transmit output, and then they're run through a number of filters and amplifiers here, and finally output on the right. And finally, in your transmit output here, your final amplifier, you've got a 3-stage power amp here. You got your input that comes in, it amplified in the 3 stages here. You've got some filtering. The output is connected into the output switching section. This is the APC unit here. The output of the final PA amplifier is connected to this connection on the left side here of the APC unit. This unit here has an SWR bridge built in, and what happens is if there's a problem with the transmission line, this will send a signal back and cut back the power in the power supply to protect the output transistors. And at the same time, the output from the transmitter goes through pin diodes here. You've got 2 of them, and what they do is during transmit they disable the receiver, it's disconnected, the transmitter's connected to the output, and during receive the opposite, the incoming signal is routed through to the RF out to the input of the RF amplifier here. In the old days this would have been done with a relay, but these use pin diodes, which is more efficient. Time for the smoke test. I have the unit hooked up to a power supply, 12 volts. I have the output connected to a dummy load, so we'll turn it on and see what happens. Well, we got a display. Oh, that's good. Squelch works. Okay, I'm going to connect it. Let's see. Oh, wait. Let's put a handy talkie on 146.
1, 4, 6, 0, 0, 0.
Nothing. Ooh, that doesn't sound good. That's definitely not good. Let's try transmitting. I'll key the transmitter. I just need a ground pin 2 here. Well, transmit light comes on. Kind of. There we go. It's growling at me. Well, let's see. Maybe we're just not on the frequency. I think what I'll do next is connect a generator up. I think I'll get my old Clegg out, because I can spin the dial on that thing and through, and I'll sweep it through here, and we'll see if we get any output on this thing. I'll try that next. I'm sweeping. I'm using a harmonic here, 3rd harmonic, and you can tell something's changing. Okay, we need to start digging into this a little better. I have 146 megahertz coming in from the antenna here, and I'm going to measure on coil. Well, actually, I'm going to measure at C102 here to make sure my signal's coming through. First, I'm going to measure it at pin 3 at J101, and we'll make sure we're getting signal in there. And we are. Okay, next I'm going to move it to C104, which is here. Still have input. This is what's nice about having a scope that'll come up into the VHF range. You can actually measure the signals here. Okay, now I'm going to make sure we've got our input signal on the lower gate of Q101. Which would be here, and we do. So the voltages are there, the input's there. Okay, now we're going to move across here, and we've got this filter. Okay, here's the drain of Q101. And we've got an amplified signal there, quite a bit actually. Okay, I'm gonna lower my sensitivity here 1 notch. Wow, it's still pretty hot. Drop it down to 20 millivolts per division. And there is the input to the helical resonators here, and that would be F101. That would be this filter here. I'm going to make sure our VCO, we've got the input or the coil side of this cap. And I have, it's diminished, but it's still there. So here is the gate of Q102, which right here is the mixer. That's the upper gate. And we do have signal there. It's a lot lower. Here's the output of the mixer. That doesn't look real stable, does it? Get a good connection here. Yeah, this might be. There we go. There's the output of the mixer. And here's the input. It's less amplitude, but you can tell it's a higher frequency. So it's mixing down, and that looks proper there. So the question is, okay, let's look at the IF out here. You can see here where I've removed the RF deck here from the unit. That's gone. This is the connection to the IF, and this is the connection from the antenna. What I've done on the output of the RF unit, here's where the antenna comes in, goes through the RF amp. Here's the first mixer. Here's your first IF out. This is 16.9 megahertz. What I've done, I've excluded all this. This has been removed, and right now I'm feeding into pin 3, the IF out, and pin 4 is ground. I'm feeding in a signal of 16.9 megahertz FM signal, and what I'm doing is I am eliminating the rest of the circuit from the IF through the audio to the speaker that's working. And here you can hear the output here. So output 16.9 megahertz, input to the IF out of the RF amplifier, and by bracketing that, that tells me I'm good all the way from the output of the RF amp to the speaker. So the problem we've got here, we're either not getting our RF in, or the VFO signal that's mixed with the RF is somehow missing. Now, one of the symptoms we have of this unit is we don't have any transmit. So I'm thinking our problem is going to be farther in towards the VCO. So that's where we're going to go next. Well, this is what happens when you work on old equipment that you're not sure of its history. Here's a coil here, this one by my thumb, and I don't know if you can see it, but it's got a cracked coil form. And somebody, I think, might have used a metal screwdriver on that coil form. So please, if you work on these units, please use a ceramic adjustment tool, because if you don't, you'll break those coils every time. So what am I going to do next? I think what I'm going to do, and I had to unsolder a bunch of shields, what I'll have to do is remove the solder 1, 2, 3, 4, 5, 6 points where this board is soldered to the shielding. And I'll have to remove the board. 2 screws come out, and the resonator here, the helical resonator, should slide out with the board. And then I'm questioning this MOSFET in the mixer. There's some problem in the mixing here. The output of the RF, I can feed in the first IF 16.9 megahertz, and it works perfect. So the problem is in this unit here. But now with this broken coil, that's going to be a problem. If I can pull this board out, what I'll do, I'll unsolder, remove. Actually, this is a transformer here. This one here, the lower one. And if I remove it, if I'm lucky, there'll be a slot in the bottom of it. I can remove the core and replace it. You know, if these don't turn easy, you want to either heat them or do something before you crack them, because once they're cracked, you're not going to remove them. That's for sure. And I don't think I have any of these transformers here. This is the transformer that's got the cracked core right here, L104. Or wait a minute, where is it? No, it's L103. L103, this transformer. This is the output of the mixer here. So this is a transformer with a bad core in it. Anyway, more work. Are these things worth all of this time and energy? Well, only if you get them working. But I like the way these things are built. They're very well built. But this thing is getting pretty old, so like all of us, it's going to need some work. Anyway, time to move on to the next step. So what I need to do is, using lots of solder wick, remove all the solder points where this board is connected to this shield, and then I've removed the 2 screws here to the resonators here, the helical resonators, so this board should pop out then, hopefully. And then if I can remove that transformer and get the core out, we might be back in business. So that's the next step. Once you get all those points unsoldered around the perimeter of the board, you can remove the shield. And here is the RF board here. You got your helical resonators in the center. Here I'll orientate it with a schematic so you can see how it's configured here. Here's the input connector, which is here. Input here. You've got your two transformer and coil here. You've got your RF amplifier. Here's your first RF amplifier. This is Q101. This is a dual gate MOSFET. FT101 is your helical resonators here. Then on the other side you've got Q102, which is your dual gate MOSFET mixer. And then you've got L103 here and L104 here, the output. Oh, I'm sorry, the input. This coil here is L104, and that's the input from the VCO, and then that's coupled up to the top gate. And then the output transformer, L103, the one with the broken core, that's connected out through pin 3. So what I think I'm going to attempt to do, remove this transformer, which means I'll have to unsolder probably about 5 or 6 pads. Remove the transformer and see if I can remove this core from the bottom. If not, that's going to be a problem. You can't get these cores out once they're cracked. They're just in there forever. So here's L103. This is the Toco coil with the broken or cracked core. I removed it. We may be in luck because looking in the bottom, I don't know if this will zoom in or not, but the bottom of the core has a slot in there. So if I can remove that core, and I'm going to be very careful, I'm going to use a little heat. There may be some wax or something in there from keeping me from removing it, but if I can salvage this coil, that'll be good. I'm going to clean this up, try to get the core out of this thing. And I don't know, it's got numbers on it. It's a Toco coil. Let's see, number, what is it? Can you even read it? Well, oh yeah, on the side here. LA 151. Sounds like a fire engine in Los Angeles to me. Maybe. Anyway, I'm going to clean this up, put it back in, and we'll see what we get. That's the next step. Well, you know, you should never use a soldering gun on a printed circuit board, of course, but sometimes you have to go against the rules. And in this case, when I got a shield that pulls a lot of heat away, I want to get in and out of here really quick. So I'm going to actually violate the rule here for a minute. And the reason I'm going to do it is I can get in and get out of there real quick, as you can see. But you have to be careful, especially what other components are around that shielding. But in my opinion, it's better to get in and get out with the heat than to conduct the heat into the circuit board. This way I was able to make a connection in just a matter of a second or so, and that's a preferable way to do it. Anyway, just a little tip. The unit is now operational, and I was able to remove this transformer that had the cracked core in it. Luckily it was just near the top. I was able to remove the transformer, turn the actual core around so I could get to the top. I also found L354 here on the VCO. This transformer had a bad solder joint. And also I found someone had screwdrivered some of these adjustments. I had to do a partial alignment. I'm going to go through a full alignment here when I get done. But anyway, test 1 2 3, test 1 2. Hello test, hello test. Now the S meter still is not working. I'm going to have to work on that. 1 2 3, test 1 2. Right now I'm running in 1.4 microvolts. Now I'm going to run it up a little bit. decrease the noise. There's 20 microvolts. I'm going to lower it now. Here's 3, here's 2, there's 1 microvolt, there's half a microvolt, so this still, it's got pretty good sensitivity. Here's 0.2 microvolts. So I'll do a sinad test on it also. Anyway, I'm going to run a few more tests. I'm going to fix the S meter, which is not working, and then do a complete alignment on it, and then I'll have to put this on the air and try it with some of my local ham friends here. So I'm going to end this now so it doesn't get too long. But thanks for coming along. It was nice to get this old unit back in operation, and thanks for watching, and we'll see you in the next one. Bye for now.